Hi, this is part 3 of matrix inverses and systems of linear equations. So this theorem is establishing what is the inverse of the product of two matrices, assuming that each of those matrices in the product, in the multiplication, assuming that each of them is invertible, assuming that the inverse of each of those exists already. So, and then the proof of this theorem relies on the definition. Inverse of a matrix is defined in terms of matrix multiplication. So this is inverse relative to the operation matrix multiplication. So if we have a matrix C multiplied by a matrix D, which equals the identity matrix, then and also we have that D times C equals identity, then this would tell us that indeed the matrix D is going to be considered the inverse of C, and also that the matrix C is going to be considered the inverse of D. So the proof that we're going to review in just a second here is going to rely on calculating products and verifying that that product equals to the identity matrix. And if so, then we have a candidate, right? So we say, all right, so we're assuming that A inverse exists, V inverse exists, and let's now check this matrix, B inverse, A inverse, which is the candidate to be the inverse of the product. Let's check what happens if we multiply that matrix times the product AB. If we do so, we can use a property here of grouping or associativity property. Matrix multiplication is not commutative, but it is associative. So we can group the terms in the middle and notice that A inverse times A is equal to the identity, and therefore now we have I times B, which would be equal to B, and then we have B inverse times B, which would be equal to I. So we have managed to start with the multiplication of the candidate matrix times A, multiplying A on the right side, and that tells us that that is equal to the identity. So now we're going to switch the order of this product. In general, matrix product is not commutative, but relative to the definition of relative to the definition or of inverse of a matrix, then there is commutativity, right? That's exactly how we define inverse of a matrix, is in relation, subject to, or in relation to the multiplication, matrix multiplication operation. So now we verify that reversing the order of these products, A, B on the left side, and then this matrix, B inverse, A inverse on the right side, we verify what that product is for reasons similar to the previous reasons that we use. These two matrices here in the middle can be grouped, and A inverse B times B inverse equals the identity. And then we have A times A inverse, which is equal to the identity matrix. So we have verified, this is the proof of this theorem, that indeed this B inverse times A inverse is the inverse of matrix of the product. So, and then you may wonder, so what happens to A inverse times B inverse? Is this equal to, what is this? Well, forget about that. Here what's going on is something that we had seen before, and more on the spirit, not exactly the same, but more on the spirit of transpose of a product. When you take the transpose of a product, this operator acting on a product is going to give you a multiplication of transposes of matrices, but they are on different orders. So the factor appears first is the factor that was second in the original product, and then the second factor is the first factor in the original product. Okay, so that is the spirit of this theorem. It has a funny name there, as you can see. Dr. Robert Wieser was the author of this book, so he likes to he has a way with words. So matrix inverse is unique. Suppose the square matrix A has an inverse, then the A inverse is unique. And if A and V are invertible, of the same size, same number of rows and columns, the product is also invertible. Inverse of an inverse equals the matrix. Inverse of a transpose works in that way, and we also discuss We also discussed this theorem that relates to the inverse of a scalar multiplication.